Hey folks, welcome to week 3. This week we're going to be talking about more advanced experimental designs. In particular, I'm going to divide this into 3 different lectures. So the first one I want to talk about is sparse sampling and related designs, as well as what are called conjunction designs. In the second lecture, I'm going to talk about functional localizers as well as periodic designs. And in the third, I'm actually going to talk about some of the topics in a little bit more detail. For instance, we're going to talk about scanning patients and the constraints that imposes on your designs and interpreting your data. But also the differences between behavior and bold. So that is to say, when do we need behavior and when do we not need behavior as long as we're doing functional neuroimaging. And as I said, those will each be separate lectures. Okay, so this first one I want to start with is related to sparse sampling and conjunction designs. And as we started out with last week, when we talked about the very fundamental designs, the really 2 most basic are block designs and event-related designs. Now, if you were to take those, a sparse sampling design is an event-related design. Okay, and the idea behind sparse sampling originally was it was a way to deal with the fact that we wanted to use acoustic stimuli in a scanner, but we had this confounding scanner noise. And in fact, early on in the fMRI days, before headphones got to be the quality that they were, and when scanners were even noisier than they are now, it was really hard to even play speech over to a participant in a scanner because the scanner noise was so loud it was really hard to hear it. So in 1999, 3 different groups came up with the same solution. And for whatever reason, Deb Hall's team seems to really get the primary credit for sparse sampling, but it's worth noting that they weren't the only people to invent it. It was clearly an idea whose time had come. And the idea here is that what's making noise in the scanner isn't the base magnetic field. That's just a quiet thing, right? What's making noise is the fact that there are gradient coils within the magnet that are changing, and those gradient coils are used to collect the data. That's how we encode space. We talked about this before. And we need that in order to know where in the brain the activation, the bold signal is coming from. So the gradient coils are changing the magnetic field, and we have a magnet within a magnet, and that generates these Lorentz forces, and that causes the noise. That's the source of the scanning noise. It's not the magnet itself, okay? But because it's in a continuous sampling scenario, it never stops. As long as you're acquiring the data, there's scanner noise going on. And if you want to have silent periods where you can play an acoustic stimulus, then you need to turn those gradient coils off part of the time and only collect less data than if you were collecting it constantly over time. So the idea is that we're going to acquire one volume at a time, and we're going to try to do it when the peak bold signal is reached in the particular area. And I'll explain this in just a second. And we're going to do that after a certain period of silence, when the gradient coils were off, and you just play stimuli during the silence. You wait until the right time to sample the bold signal, then you turn the gradient coils on specifically for that period. And then you just sort of wait for all of that material to return to baseline, and you can repeat. So let me just sort of illustrate that. This is the basic idea, right? So imagine on the bottom of the screen, you're looking at a stimulus that's being played for 6 seconds, and this would be some sort of acoustic stimulus. It could be somebody speaking, it could be tones, it could be any number of auditory stimuli. And then there's a long blank in between the end of that stimulus and the start of the next stimulus, where you then start to repeat. And what would happen is you would expect in auditory areas or parts of the brain that are responding to this auditory stimulus to evoke a bold response that is a little bit delayed and dispersed relative to the stimulus because of the hemodynamics, right? So that is to say, it doesn't shoot up instantly as soon as you hear an acoustic signal because the blood flow has to increase in order to measure a change in the bold signal. And that's what you're seeing up at the top. So in this kind of a scenario, if you were able to sample the data at the peak, which is what's shown between those dotted lines, then that would be ideal. You'd know that that's the time window where the bold signal has more or less reached its peak, so that's the maximum signal that we can raise. And if we have a 3-second window that we can acquire one whole brain volume during that, then we can collect the data in blue with a minimal contamination from the noise of the scanner. So by turning on the gradient coils at this point, we're introducing scanner noise. But of course, that scanner noise takes a little bit of time to ramp up as well, and you can see that in the red lines in the top part of the plot. So there's the maximum blue signal, which is the signal due to the auditory stimulus, and a relatively minimal amount of noise, that is acoustic stimulation due to the scanner itself. And then what happens is you collect that one volume, and then you just wait and let everything return to baseline. Okay? So in other words, in this case, we have a much longer repetition time. Rather than having a typical 3-second repetition time, which is what we would do from one volume to the next if we were collecting in a continuous fashion, we actually have a 21-second repetition time. That is to say, from the start of one volume of acquisition, 1 point in red, to the start of the next one, 21 seconds are passing because we're allowing all of the signal that's been generated by the various sources of acoustic information to return to baseline levels before we start again. So in a real way, this is a very classic event-related design. We have one event that's happening over a long period of time so that we can allow the bold signal to return to baseline. And the interesting thing about a sparse sampling paradigm like this is that we separate out the TR, the repetition time, from what we're going to call the TA, the acquisition time. So in this case, we're still doing a 3-second sample of the whole brain, and that's the acquisition time. And normally the acquisition and the repetition time are the same because normally you just immediately repeat them. In a sparse sampling time, you don't, right? In a paradigm like that, what happens is you acquire that one volume, then you wait 18 seconds until you acquire the next, or sorry, 21 seconds until you acquire the next one. Now, let's just think about what that means, right? So I've sort of blithely said that you just go to the right period when you've expected the maximum hemodynamic response in order to sample the curve at its peak to maximize your signal. But clearly that's going to be dependent on knowing that evoked hemodynamic response function. So we make assumptions about the shape of the hemodynamic response function, but they are just that. They are assumptions, and it's not going to be the same in each person. It's not going to be the same in each part of the brain. So it's unbiased to make an assumption that it sort of fits a canonical response. But that doesn't mean that you're necessarily going to get optimum signal from each person in doing this. So the fact of the matter is, whenever you're doing sparse sampling, you are making an implicit assumption about the shape of that hemodynamic response function. And if you don't have any other information, that's about the best you can do. But if you're really concerned about increasing your statistical sensitivity, one thing you might think about doing is actually measuring evoked hemodynamic responses in each of your participants in auditory areas, or whichever part of the brain you're interested in, to maximize the design timing, right? So it may be that I am reasonably old and fat and smoke and don't exercise and therefore have very sluggish hemodynamic response function, whereas you're young, fit, and healthy, and therefore you have a faster hemodynamic response function. So we might need to tweak the design from person to person to make sure that the repetition time is such that we're acquiring the peak response for each individual, right? And that would be a fairly significant design consideration to take into account. If you don't do that, and you don't have to, most people don't, then you need to be aware that by definition, you are limiting the statistical sensitivity in an unbiased way, but nonetheless, it's suboptimal. The other thing that's worth bearing in mind is that 3-second acquisition time is to do like a whole brain acquisition. But we've already talked about the fact that you can do bias sampling of whole brain this way because the hemodynamic response function isn't the same in each part of the brain because they happen at different points in that 3-second window, right? So what you want to make sure you're doing is you're collecting the part of your brain or the section of the brain that's peaking within the HRF at that point. And maybe it's not the bottom, maybe it's not the top. I mean, in traditional form, the auditory cortex is very sort of middle of the brain, right? It's at the border of it's around the sylvian fissure, so it's at the border of the temporal lobes where it goes into the frontoparietal regions. So if you're doing an ascending or a descending one, in either case, you're sort of getting this at about the middle of the time window, which is great if that's what you're interested in. If all you care about is what's happening in auditory cortices and the surrounding areas, which are also secondary and tertiary auditory cortices, but it's less good if you're interested in not only what's happening in auditory areas, but what's happening in other regions. So for instance, if you're interested in speech and it's evoking responses in some sort of midline superior frontal cortex, well then that, that's all the way up here. That's a very different situation than what's happening at this point, and it's still different than, say, basal temporal lobe, which could also be activated by speech. So depending on how you do this, you may need to take seriously the fact that you've optimized your sequence for one part of the brain and not others. That comes at the expense of others. So if all you care about is auditory cortex, and that was exactly how sparse sampling was designed, then fine, you're probably okay. If you're also collecting the rest of the whole brain data with the idea that you're interested in auditory cortex and, other areas, superior areas, inferior areas, wherever they may be, then you need to know that you're going to biasing your sample against collecting the data in the optimal region if it's optimized for auditory cortex. By definition, it's then not optimized for other areas. And of course, related to that is that if this is a purely event-related design, then statistical sensitivity is an issue just to begin with, right? I mentioned last week that an event-related design has, maybe, a fifth the sensitivity of a block design, and that's in sort of the best case scenario. Well, if you're already at 1/5 of the sensitivity of what you could do in a block design, and then you're, sort of making it less efficient by not sampling different parts of the brain with their optimal HRF timing, then, it's even worse. And the thing that you need to do in that case is just collect a lot more data. Presumably you want a lot more data per person, but you need to be aware that if your repetition time is 20 seconds for each stimulus, this is a very long experiment. So the more conditions you have, the more stimuli you need, the longer the experiment takes, the more bored participants get. You can see that there's a causal chain of issues that need to be dealt with here. The alternative might be to just collect an awful lot of participants, but not a huge amount of data from each participant. And that's fine too, but again, you have resource limitations, both in terms of time and money, in terms of how much data you can actually collect from, different in one experiment. The other thing is, in this classic version, there is no temporal jitter. You can see that the repetition time between acquisitions is 21 seconds. And that's when we're doing our stimuli as well. So the one thing I said before was that you should never make your inner stimulus interval an integer multiple of your repetition time. But that's exactly what this is in a sparse sampling design. And the reason for that is because we're assuming the bit that we care about is auditory cortex, and it's being unbiasedly sampled because it's in the middle of your head. But that's just not always the case. People are interested in measuring other areas. And in fact, people have taken this kind of a design and used it for other things, so not just auditory regions. So one of the things that people have done is when they've tried to combine transcranial magnetic stimulation, or TMS, with fMRI, then you have a magnet that's put in the scanner, for instance, next to somebody's head, that's actually creating stimulation in terms of magnetic pulses to change neural activity in certain underlying regions, and then looking for the effect of that using the fMRI to measure the change in activity in the brain. Well, you can't have the TMS coil pulsing at the same time the gradient coils are on. There's a physics issue here where they start to interfere with one another. They ruin the data. They change the effect of the TMS. So in that case, you actually need to use a sparse sampling paradigm, not because you care about the sound, but because you don't want the gradient coils on when you're using TMS to stimulate. And in that case, normally you aren't, for instance, interested in auditory cortex. It depends on what area of the brain you're stimulating and what areas it's related to. So in that sort of a scenario, understanding the fact that you have not built in any temporal jitter typically, and that you might be suboptimally sampling the hemodynamic response function as a result of that, is a major concern, and that's something that you need to deal with during the design phase. There's no reason you can't make your inner stimulus interval varied, but again, the consequence of that is you're going to need to collect additional data. One of the other things that people sometimes say is, well, couldn't I get more trials in if I just sort of shorten the acquisition time? I mean, if all I care about is auditory cortex, I can get that from like maybe one plane through the supratemporal lobe, maybe 2 planes. I don't need to collect the whole brain data. And that's true, but it amplifies the problem of whether or not you've gotten the peak of the hemodynamic response function. So if you collect whole brain data, then the odds are that you are going to get something in that 3-second window. But if you get it down to, say, 500 milliseconds, well then, what are the odds that that 500 milliseconds includes the peak of the hemodynamic response function? They're much smaller now. and therefore you're more susceptible to these sampling biases. There are other reasons why that's not optimal either, that have to do with image preprocessing. So if you can collect whole brain data, I think you'll find that in general it's easier, even if you're not planning to use all of that data. Here's just an example of this, and this is a giant old study that I ran, at the turn of the century or something, where we were looking at laterality in primary auditory cortex. So in basically all species that have been tested, despite the fact that there's a lot of mixing of the signal from your ear to the brain, you still see a dominance for where your right ear shows a larger response in left primary auditory cortex, your left ear shows a dominant response in right auditory cortex. And I suspect, because the video is reversed, it's going to look like I don't know left and right, but honestly I did pick the right sides there. But the important thing here is that hadn't really been tested in humans, and the key is that you have to stimulate only one ear. Acoustic noise from the scanner is by definition stimulating both ears, so you need to do it during a silent period. So this is a kind of experiment that you would use a sparse sampling paradigm for, and that's exactly what we did. We played sounds to either the right ear or the left ear, and then we measured the response in auditory cortex, which is shown here in this image. This is actually sort of an inflated brain because Heschel's gyrus, which is the site of primary auditory cortex, is deep in the sylvian fissure and hard to see otherwise. So we've partially inflated the brain so that you can see Heschel's gyrus. And then you can see the activations in the right and the left hemisphere to monaural stimulation. But the plots basically show that when you stimulate the right ear, you get contralateral activation. That's what the CO is there, across individuals. So that's a bunch of participants. All of them are showing this contralateral activation. So you stimulate the right ear, you see a stronger response in the left hemisphere. You stimulate the left ear on the contrast, and you see stronger response ipsilaterally. That is to say, you still see a stronger response in left primary auditory cortex in human beings, which is interesting because it's different from what we see in other species. And whether or not it holds up to be true, I mean, there's some studies that have also found the same thing, but I think it's an interesting and questionable finding at this point. If it's true, it may relate to the sort of left hemisphere dominance that we have for language, but it's an interesting question that's still being explored. But it's exactly the kind of auditory paradigm that sparse sampling was designed for, and it sort of shows how it can be used in that kind of a context. Okay, so I've already talked about these implications. This is just intended as a summary. It's an event-related design because each trial is independent. That actually is going to have some effects on the way we analyze the data as well, because we don't have a time series in the traditional fashion here. It requires a very long TR, repetition time, but a relatively short acquisition time. That is to say, we normally use the 2 to 3 second whole brain acquisition. It does make implicit assumptions that you know something about the regional specificity of the hemodynamic response. If you don't, and you use a canonical hemodynamic response, that's fine, but you just need to be aware that it may be suboptimal. Also, if all you care about is auditory cortex and you're using this kind of canonical HRF, probably you don't have to worry about jitter because it's in the middle of the brain and you're using an ascending or descending sequence, it's fine. It doesn't really result in any significant bias. However, if you're interested in other parts of the brain, or you're interested in auditory cortex and other parts of the brain, or you're using an interleaved sequence, then for sure you definitely want to build in some temporal jitter. You want to make sure that, as always, you don't have an interstimulus interval that matches your repetition time, your TR. Because if you do, you end up with this bias sampling of the HRF. And that means that you do end up with these very long paradigms in order to collect enough data. And then finally, as I said, there are going to be various implications for the analysis. It's going to have what are known as T1 longitudinal effects, which we'll talk about next week. It's going to affect temporal autocorrelation, which we'll talk about more when we talk about first level analyses. And it's going to have important implications for statistical power or sensitivity. We've talked about the sensitivity issues. The others will come up when we get to those topics in the following weeks. Okay, so another more advanced design is something that's known as a conjunction design. These were more popular in the late 90s, early 2000s. They're less popular now, but when you say that, it's not strictly true. Calling it a conjunction design kind of went out of fashion, but people still use conjunctions all the time. They just tend to do it a little bit more informally. So let's talk about what they are and what they should be and how you would do it right. Okay, so the idea behind a conjunction design is it's a way to deal with the sort of problem choosing baselines. So we talked a little bit about the importance of when you're going to do a high level baseline, if you're making an assumption of pure insertion, you could be assuming these two things only differ by this one factor and be just simply wrong. And therefore, when you do your analysis, you discover they don't differ at all and you've got nothing. The alternative was to use lower level baselines, but then you're not really limiting the difference to the one thing you care about. There's a whole bunch of things that are going on. Conjunction design is a way of using multiple comparisons with low level baselines to try to get around that phenomenon. So I've illustrated it here in this slide where there are 3 comparisons. We're comparing conditions A to B, C to D, and E to F. And what we're interested in is where do they overlap? Where are the activations in common? So let's just try to make that a little bit more concrete. If I were interested in something like object recognition, it's really challenging to sort of say, well, what is the 2 things that you would compare that tells you exactly object recognition and nothing else, right? So for instance, I might say, well, look, naming pictures would be good for that because I could name pictures or I could name words. And in one case, I really care about recognizing the object, so it's the only way I can get to the right name. But in the case of words, I don't need to recognize it. I can just sort of sound it out and I'd still get the word. I don't have any visual object recognition going on. And that's true. That is one of the things that differs between them. But the other is, name retrieval. Once you recognize the object, you have to retrieve a name in a picture case, but not for words because you've sounded it out. The name is already there. It's intrinsic to that process. And of course, there are low-level visual differences as well. I mean, object recognition is very different than visual word recognition. They have different spatial characteristics, different contrast characteristics, etc. So there are both high and low-level differences there as part of that contrast. If we were to say, add another contrast and say, well, what about when you recognize objects versus recognizing faces, right? So I'm just going to ask you to do a task where I'm not asking you to say the name of anything. So we're going to get rid of all those name retrieval aspects. I just simply want you to push one button if it's an object and one button if it's a face, right? And that requires object recognition, or at least recognizing that it's not a face. But again, there are differences here in terms of the spatial characteristics. Faces tend to be largely symmetric. They happen to have particular contrast patterns, etc. Again, which are different between them. It's not just down to the fact that you're recognizing an object. Well, what if we added like a third thing, like just simply viewing objects versus viewing spatial patterns that have exactly the same characteristics of the object? So you can make noise patterns that don't look like objects, but have the same spatial frequencies, have the same spatial contrast. In that case, we're dealing with all those low-level compounds, but we still have object recognition versus not object recognition, which is one thing we can look at. So if you look at all 3 of those contrasts, they vary in terms of what aspects they have in common. But the one thing that I've said that they all have in common is object recognition. Each of them has other things, but those other things aren't held in common. So if we were to then say, look, if I look at this contrast of A to B, naming pictures to words, and I overlay it with what I see for recognizing objects versus faces, and then I overlay it again with viewing objects versus, context noise that's characteristic, and I said, well, which parts of the activation were held in common over those 3? Well, those are the things that might very well be involved in object naming or object recognition, independent of those other characteristics. And that's the idea with a conjunction design. Okay, the idea is that by looking at these various contrasts, you look for what they have in common, and that common underlying activation may very well be due to a common underlying information processing characteristic that you're interested in. And this is an example that I've mentioned before. They didn't call it a conjunction design, but it's still a good example of it. This is the study that Stan DeHaan's group did, where he was looking at repetition priming because he was trying to figure out where in the brain was sensitive to orthography, or your ability to recognize visual words. And he reckoned that one thing that they would have in common is that it shouldn't matter whether the case of the prime word and the target word, shown here in, for instance, an uppercase radio and a lowercase radio, were the same or different. You still recognize them as radio, right? So that would be a place where you would expect to see knowledge of visual words, but of course that would overlap with if they were the same case. If they were both lowercase, you would still see this priming effect because of course it could be due to visual features, but it could be due to the fact you recognize them as the same word. So in other words, this is a conjunction design. They're looking for when you compare same case priming to different case priming, so same case repetition priming to same case non-repetition versus alternating case priming to alternating case non-repetition, right? So you have these two contrasts, and what you're interested in, you can see it here in this plot, is the difference between the different words and the same words independent of case, and you're looking for a common area. And what they found in this case was this ventral occipital temporal region. So this is a good example of a conjunction design. But it also illustrates one of the difficulties with a conjunction design, which is although this is exactly what they designed it for and it gave them a really interesting result and it's proven to be something that's very much in everyone's focus when it comes to reading, what is this area doing? It doesn't mean that this is an area that's dedicated to reading, right? So let me just give you another conjunction design. And this is one that Kathy Price and I did, again, years and years ago at this point. But these are 4 contrasts, all of which activate that same part of the brain, even though none of them are due to reading. So for instance, if you ask people to name a picture of a helicopter compared to visual noise, you activate that part of the brain. If you ask people to look at a picture of a tiger and say tiger versus reading the word tiger and saying tiger, you activate it even more strongly for the picture than the word. And again, that would be hard to explain solely in terms of reading. But it's even more than that. If you ask people to look at pictures of different size items, like the broom here, then if you ask them to do a size comparison on a meaningful picture relative to illustrating what kind of action they would do with it, you see activation in this part of the brain as well. So there's no naming component here whatsoever. This is simply some form of object recognition. And then finally, you can do the same thing for things that you've never even seen. These objects at the bottom, you can imagine asking somebody how to manipulate it. You could do it something like that relative to how big or small it is, and you get activation in the same part of the brain. So what's really interesting here is this is a classic conjunction. These are 4 contrasts that are all independent of one another, and they all show activation in this part of the brain, and none of them appear to be specific to reading. In fact, what I would argue is actually happening is that this is part of the brain that's very sensitive to visual structure, and reading relies on visual structures. That's how you tell letters apart from one another. But object recognition relies on visual structure as well, and particularly, it doesn't matter whether you are literally recognizing an object and the ability to name it, or you simply recognize it enough in order to, say, manipulate it. Regardless, you're getting this common activation. So I'm suggesting a different alternative to this kind of result than what DeHaan and his colleagues have suggested. And the reason this is important is not because this particular theory is relevant to you, but it raises the point that when you're interpreting these results with a conjunction, you have to be careful not to say that what you see is specific to your particular idea, right? Conjunction didn't test that. All it tested was what's in common between the contrasts. Right, so that's the first and one of the most important design implications. The other one that we have to say is that in order for this to be valid, the contrasts have to be independent of one another. They have to be orthogonal, if you want to be more technical. So what do I mean by that? I just mean that if you have a design like this where people are listening to ambiguous sentences and then there's a rest and then unambiguous sentences, then you might think, well, what do we have in common for ambiguous and unambiguous sentences? That would be a good conjunction. But the problem here is this is not an orthogonal contrast because rest is the same in both cases. So for instance, let's just say you had a paradigm like this where A gave you a little bit of an effect and B gave you a bigger effect, but rest gives you some sort of negative, like decrease in bold signal. Then all of a sudden, the difference between A and R and B and R is a lot. There's all sorts of things that might be going on there. Is that because A and B are very common? No. It's because there's a negative activation, a deactivation for rest. These contrasts aren't independent of one another because they're using the same baseline. Well, how would you modify a design like this? Well, you could just do it in different runs, right? So if you had a run where you tested A and a run where you tested B, well then by definition, even though there's rest in both of them, they're different data, and therefore they are independent of one another. So that's all I really wanted to say about sparse sampling and with respect to conjunction designs. There's a lot of material here, but I think that's where I want to stop before we move on to the next lecture.